Mr. Yandell here. Last few days we've been working on a lab, and you've been filling in a chart and making a couple graphs for us. But that's not the end of the lab. There's a whole group of things that need to happen before we finish. So let's assume you've already filled in the chart, you've already made the two graphs, and now you're ready for the next step. Here's what we need you to do. Suppose that that's the tabletop, and this is the board that you've been dragging the wooden block across. What we're interested in now, since you know the angle in here, theta, and since you know the displacement that you've been doing with the block up the incline, we're now interested in the height at the end of the incline, h. So what we're challenging you to do, knowing d, knowing theta, and having the trigonometric skills that you have, find h. So you're going to take that chart and add an extra column. We're going to have an h column now, and we're going to have that measured in terms of meters. And we'll worry later with why this screen just went dark. Oh, there it comes back again. That's good. The next step, after you've made this the next column, is to calculate mgh, which is the potential energy. And for some reason the screen's going dark, and we hope you don't notice that when you look at this. So now you're going to have the heights all the way down, and now you're going to have potential energy all the way down at the end of the thing. So once we have the height and we've calculated the potential energy, mgh, then you have a graph to make. You're going to have a graph to make of potential energy to the angle theta. And that will be the end of step one. The next step is to compare a couple of your graphs. You just made a graph of potential energy to incline angle, and previously you had made a graph of work to that same set of angles. And what you should notice, if this turned out the way we would expect, you should see that the graph here and the graph here are quite different. The values of work up the incline are greater than the potential energy. And that's what's going to be of great interest to us. Suppose we just took one value here and here, the same angle, and we compared, and we find out it takes more work to drag the block up the incline, that would be this one, than it does to take the block and lift it straight up to the top of the incline through the gravitational field. I'll leave you to think for a second about why there's more work up the incline than straight up. That'll show up on step 3. Well, hopefully you realize that the difference between sliding the block up the incline and raising it straight up is the force of friction on the incline. So now you have a little bit of a challenge. We know that the force of friction is calculated with mu times the normal force. Trick for you is to figure out how to calculate that normal force. We're giving you that mu is 0.44 between the block and the incline. How can you calculate the normal force? Look back at your notes, figure out how to do that, do a little searching till you know how that works. Once you've calculated the force of friction, here comes the final part. Da-da-da. The work done by friction would be the force of friction times that displacement. So once you know the force of friction, you can use it right here. You know the displacement up the incline, and if we're lucky at all, this force of friction, this extra work that's right here, will match up with our graphs and make up the difference between the potential energy and the work on those two incline graphs. So we're going to try to see if this is the difference between the two graphs, and that should give you some idea of what our hypothesis might be by what you heard me just say. I'll leave you to ponder that.